Okay, 2.51. This is a free fall problem where we are treating a classical system via quantum mechanics, just to show that sort of quantum mechanics actually does carry over validly into sort of classical mechanics, although significantly more complicatedly compared to if you were just to treat free fall via kinematics. So we want to show that this given wave function here satisfies the time-dependent Schrodinger equation for a particle in a uniform gravitational field, V equals mgx. So this is effectively just a particle dropping from some point and is subject to gravity. So this is typically one of the first situations you would treat when you just start learning physics. Just sort of a particle dropping, like a ball dropping off of a cliff or something like that. And psi naught x of comma t is the free Gaussian wave packet from equation 2.111. And then finally, we want to also find the expectation value of x as a function of time and comment on the result. So let's start off with definitions here. Psi naught of x comma t from the free Gaussian is defined as psi naught of x comma t equals 2a over pi to the power of 1/4 times 1 over the square root of 1 plus 2i h bar at, all divided by m, multiplied by the exponential of negative a x squared divided by 1 plus 2i h bar at over m. So if we define it this way, note up here that our x argument is replaced with x plus half gt squared. So psi naught of x plus half gt squared comma t is then going to be defined as 2a over pi to the power of 1/4, 1 over the square root of 1 plus 2i h bar at divided by m times the exponential of negative a times x plus half gt squared all divided by 1 plus 2i h bar at divided by m. And if we take this and shove it into the actual wave function equation that we want, psi of x comma t equals 2a over pi to the power of 1/4, 1 over square root 1 plus 2i h bar at divided by m, multiplied by the exponential negative a x plus half gt squared over 1 plus 2i h bar at over m, and then multiplied by this second exponential term, exponential of negative I mgt over h bar x plus 1 over 6 gt squared. And at this point, we just want to plug this into the time-dependent Schrodinger equation and verify that that's actually correct. So the time-dependent equation is going to be I h bar partial psi with respect to t is equal to negative h bar squared over 2m times the second partial of psi with respect to x squared plus v times psi. So we have v is equal to mgx, so we just have to replace v with mgx. In which case now it's just a matter of taking these partials, which is by no means easy considering how complex of a beast this equation actually is. Let's do a little bit of rearranging first off, just to make this a little bit simpler on ourselves. I'm gonna combine these two exponents. Take the minus at the front and just move it over like this. So at this point, we now have to take these derivatives, which is exactly what we will do. Okay, so hopefully, just from looking at this mess of an expression, it's very obvious to you that taking time and position derivatives for this is going to be really painful. So instead of, torturing ourselves and going through the process of deriving this thing with respect to x twice, and then with respect to time, and verifying this super complicated expression, we can make things a little bit easier by recognizing that sort of the exponential has this x plus half gt squared term that comes up a lot. So we can do a change of variables from x and t to r and s, where I can say that r is equal to x plus 1/2 gt squared, and I can say that s is just directly equal to t, in which case psi of x comma t is then going to transform into psi of r comma s, and all the partial derivatives can transform via the chain rule. So the partial of psi with respect to time can then be rewritten as partial psi with respect to r, partial r with respect to time, plus partial psi with respect to s, partial s with respect to time. And recognize that since s is directly just equal to t, and for r, well, dr with respect to time, that's going to be gt. So this is going to be d psi with respect to r multiplied by gt plus d psi with respect to s, and then ds by dt, well, s is equal to just t, so ds by dt is just going to be equal to 1. And then we can do a direct transformation again, so this is just equal to partial psi with respect to r. T is directly equal to s, so multiplied by gs plus partial psi with respect to s. Similarly, the partial of psi with respect to x is going to equal partial psi with respect to r times partial r with respect to x plus partial psi with respect to s times partial s with respect to x. This term is going to just equal 0, so we're left with d psi by dr times dr by dx, which is just going to exactly equal 1, so we're just left with d psi by dr. The second derivative of psi with respect to x squared is going to be the same sort of operator, chain rule operators, but this time acting on the partial psi with respect to r. So d by dr, dr by dx, plus d by ds, ds by dx, all acting on d psi by dr. So if we do it like that, once again, ds by dx is 0, dr by dx is 1, so we're left with d2 psi by dr squared, because remember, ds by dx is equal to 0, so this term cancels out. What we're left with is this. The dr by dx becomes 1, and then the d by dr just goes directly onto the d psi by dr, which gives us a second derivative. So now it's just a matter of redefining our wave function in terms of r and s, and using these properties to redefine our Schrodinger equation. So let's do that now. Psi of r comma s is now going to equal. So we have, let's see. Let's have psi naught right here redefined, because this is originally in terms of x plus half gt squared comma t. So this gives us a perfect excuse to replace this this term right here with just r. So we now have psi naught of r comma s. And this is multiplied by the exponential, so multiplied by exp of, this is going to be negative I mgt over h bar, and then multiplied by just, let's see, so this is x plus 1/6 gt squared. Here we have x plus 1/2 gt squared, so x plus half, let's write this in blue to figure out what this is going to equal. X plus half gt squared is going to be added with some other function, f, and this is going to equal x plus 6th gt squared. So the function is going to equal 6th gt squared minus half gt squared, which is going to equal negative 1/3 gt squared, I believe. 3, 3, 6, 1/2 1/6. Yeah, and then x plus 1/2 gt squared plus something is going to equal x plus 1/6 gt squared. So get rid of the x on both sides. F is equal to 1/6 gt squared minus 1/2 gt squared. 3, 6, negative 2, 6, 1/3. Yeah. Okay, so this is actually going to be replaced. Instead of x plus 1/6 gt squared, we can replace this with just r minus 1/3 gt squared, but we're replacing t with s, so we're going to turn this into s squared. Same thing over here. We're going to replace the t here with an s and close off the exponential. And if we plug all of these identities into the Schrodinger equation, what we're going to get is, let's see, we want to verify this new equation, I h bar d psi by dt, which is going to be this, so d psi by dr times gs plus d psi by ds. And this is going to equal negative h bar squared over 2m multiplied by second partial of psi with respect to x. So this becomes d2 psi by dr squared plus mg, and then we're replacing x, so this is going to become r minus half gt squared times psi. So what I'm doing is I'm taking the Schrodinger equation up here, I'm replacing all of the inner terms and also x terms with these identities along with this, and this gives me this new equation here. So now I have a significantly simpler expression, and I want to plug everything here into the results. And more conveniently, actually, we don't even need to write out psi not fully, and you'll see exactly what I mean in a second as we start plugging in these derivatives. Okay, so let's start by taking the derivative of psi with respect to s. So let's do this in green. Partial psi with respect to s is going to equal, looking up here by chain rule, I'm going to get partial psi naught with respect to x times exp negative I mgs over h bar times r minus 1/3 gs squared. And then adding with psi naught r comma s, the exponential as before, negative I mgs over h bar times r minus 1/3 gs squared, and then multiplied by the derivative of this inner term with respect to s. So this is going to give us, let's see, multiplied by ds of negative I mgrs over h bar plus I m g squared s cubed over 3 h bar. And then we can sort of recognize that sort of this term, the beginning of this term right here, this starting term, this is exactly just equivalent to psi of r comma s, because if we look up, you know, we have this expression right here, which is exactly that. So we can simplify this a little bit, and we can rewrite this as partial psi with respect to s is going to equal partial psi naught with respect to s times the exponential negative I mgs over h bar r minus 1/3 gs squared plus psi of r comma s, and then multiplied by, let's see, what is this going to give me? Negative I mgr over h bar. Yeah, mgr over h bar plus I mg squared s squared over h bar, because the 3 gets brought down and cancels. Is that correct? Plus I mg squared s squared over h bar. Yeah, so this is our partial with respect to s. Now let's do partial with respect to r, which I'm going to do in blue. Partial psi with respect to r is going to equal partial psi naught with respect to r multiplied by the exponential exp negative I mgs over h bar r minus 1/3 gs squared. And then the same thing as before, so we're going to have this term over here, which basically is just going to equal psi. So psi of r comma s, and then the derivative of this thing, but this time instead of with respect to s, we're doing it with respect to r. So that's going to give us negative I mg s over h bar, and then the last term here has no r dependency, so that just goes to 0. So if I want to rewrite this to make it a little bit nicer, I can rewrite this as minus I mgs over h bar multiplied by psi of r comma s. And then we can move on and take the second derivative, d2 psi with respect to r squared, which is going to be just the derivative of this term. So if we want that, let's see, we're going to have to take d2 psi naught by dr times the exponential, negative I mgs over h bar times r minus 1/3 gs squared, added with d psi naught by dr exp, negative I mgs over h bar r minus 1/3 gs squared. And then this time, this is going to get multiplied by, let's see, the derivative of this, which is going to be negative I mgs over h bar. Is that correct? Derivative of the exponential inner term, which is going to give me this with respect to r. Yeah, and then finally subtracted by I mgs over h bar d psi with respect to r. So if I plug this back in, this inner term is going to become subtracted by d psi naught with respect to r exp, negative I mgs over h bar r minus 1/3 gs squared, where I'm pulling it from this term. I'm replacing the d psi by dr with this term. And then multiplying by negative I mgs over h bar. Let's see. And in fact, if I'm going to pull the negative in, I'm just going to do this instead. Get rid of the negative at the front. And then this is being subtracted by I mgs over h bar psi of r comma s, and then once again multiply by negative I mgs over h bar. So this is going to give me, let's see, this term right here matches this term over here. So these two can combine, and what I'm left with is that the second partial of r with respect to psi is going to give me the front term, d2 psi naught by dr exp, negative I mgs over h bar times r minus 1/3 gs squared. And then these two terms, which combine, this top expression and this bottom expression. So this is going to give me, let's see, minus 2I mgs over h bar partial psi naught with respect to r times the exponential exp, negative I mgs over h bar times r minus 1/3 gs squared. And then finally, this back term, which is going to be, the two negatives make it positive, but the two i's make it negative again. So minus m squared g squared s squared over h bar squared, and then multiplied by psi of r comma s. Okay, and that constitutes our three derivatives. Next, let's plug them into the Schrodinger equation, or the modified Schrodinger equation in terms of r and s that we have. Okay, so this is our modified Schrodinger equation. Now let's start solving. So I'm going to do the left side first. So we have I h bar, and then multiplied by d psi by dr, which we have up here in blue. So I'm going to copy paste this and move it down. And this is getting multiplied by gs. And then we're adding d psi by ds, which we have here in green. So now it's just a matter of simplifying this down. So let's start with the top. So we have I h bar, and then we have gs d psi naught by dr exp negative I mgs over h bar times r minus 1/3 gs squared. And then we have minus I mg squared s squared over h bar psi of r comma s. And then we're adding the same thing as before, so plus, and let's do partial psi naught with respect to s, exp negative I mgs over h bar times r minus 1/3 gs squared. And then let's distribute this out. So minus I mgr over h bar times psi of r comma s. And then plus I mg squared s squared over h bar times psi of r comma s. And we see here that these two are equal and opposite, so they cancel out instantly. Now, what we're left with after multiplying the I h bar onto each term is going to be I h bar gs partial psi naught with respect to r exp of negative I mgs over h bar times r minus 1/3 gs squared. And then plus partial psi naught with respect to s exp negative I mgs over h bar times r minus 1/3 gs squared. And excuse me, I forgot to include the I h bar at the front. And then finally, two i's make a negative, so the two negatives cancel, so we're adding. H bar cancels out with the h bar at the bottom, so plus mgr psi of r comma s. So this is the left side of our expression. Now let's do the right. Okay, now let's do the right side, which I'm going to do in brown. So we have negative h bar squared over 2m times the second derivative with respect to r. So negative h bar squared over 2m. And then the second derivative, which we have up here as this big mess of a function. And I've also I've fixed it a little bit. I left out the 2 in front of the sort of r when defining the second notation right here. I included the 2, but that's really the only thing that I changed. Okay, and then let's see. We are adding this expression, so plus mg of r minus 1/2 gt squared multiplied by psi. So now it's just a matter of multiplying everything out. So at the front here we have, it's going to give us, let's see, negative h bar squared over 2m d2 psi naught with respect to r squared times exp negative I mgs over h bar r minus 1/3 gs squared. And then over here we have, let's see, the 2 cancels, the m cancels, one of the h bars cancel. So we left with plus I h bar gs, I believe. So the h bar cancels, the 2 cancels, the m cancels. So we're left with a single h bar. Yeah, so plus I h bar gs d psi naught with respect to r times the exponential negative I mgs over h bar r minus 1/3 gs squared. And then the final term plus, let's see, one of the m's cancels, h bar squared cancels, so we're left with mg squared s squared over 2 psi of r comma s, and then we're adding mg r psi minus mg squared, and then the t gets just replaced directly with an s divided by half. So I forgot to do that earlier, but really since t is equal to the s, the notation is kind of trivial. Psi of r comma s. Immediately I see that these two terms are equal, so those cancel. And now let's compare to the top expression. So we have mgr psi of r comma s, which cancels out on both sides. We have this, let's see. Yeah, we have I h bar gs partial psi naught with respect to r exp. And so this term cancels out with this term. The only term we have left, which doesn't seem to match, is this I h bar d psi naught with respect to s, excuse me, and then this negative h bar squared over 2m second partial of psi naught with respect to r squared. So in order for this modified Schrodinger equation to actually work, and therefore for this wave function to be accurate and therefore correct, these two terms have to equal each other. So our new requirement now is that negative h bar squared over 2m times the second partial of psi naught with respect to r squared has to equal I h bar partial psi naught with respect to s. So what we're saying is that sort of this expression up here has to equal this expression down here. And if that's true, then the Schrodinger equation terms all equal, in which case our wave function is indeed valid. So our next step now is to verify that this is actually true. And going back up, we're going to redefine psi naught here. So psi naught of r comma s is equal to 2a over pi to the power of 1/4 times 1 over the square root of 1 plus 2I h bar as over m, multiplied by the exponential exp negative a r squared over 1 plus 2I h bar as over m. So now we just have to verify that these two expressions are equal, so that's exactly what we're going to do next. Okay, starting with the partial of, let's do r first because that's easier. So partial of psi naught with respect to r, that's going to give us 2a over pi to the power of 1/4 at the front. We have our same root 1 plus 2I h bar as over m. And then we have the derivative of this exponential. So the exponential remains unchanged, negative a r squared over 1 plus 2I h bar as over m. And then we have the derivative of this with respect to r. So this is going to give us negative 2ar over 1 plus 2I h bar as over m. So we see here that this front term is unchanged. So we can rewrite this just as psi naught of r comma s multiplied by, and you know what, I'm going to change the order around. It's going to equal negative 2ar over 1 plus 2I h bar as over m multiplied by psi naught. Next, the second derivative, partial squared psi naught with respect to r squared, is going to give us, by chain rule, we have negative 2a over 1 plus 2I h bar as over m multiplied by psi naught of r comma s, and then subtracted by 2ar over 1 plus 2I h bar as over m partial psi naught with respect to r. So then we just plug this in again, and this is going to give us negative 2a over 1 plus 2I h bar as over m times psi naught of r comma s, and then subtracted by, and in this case actually we're going to add it, so plus 4a squared r squared over 1 plus 2I h bar as over m squared psi naught of r comma s. Is that correct? Yes, it is. Okay. Now, the harder one, the derivative with respect to s. So partial psi naught with respect to s is going to give us 2a over pi to the power of 1/4, and then the derivative of s of 1 plus 2i h bar a over m times s to the power of negative half multiplied by the exponential and then we're adding 2a over pi to the power of 1/4 times 1 over root 1 plus 2i h bar a s over m multiplied by the exponential negative a r squared over 1 plus 2i h bar a s over m, but this time we're deriving the inner term of the exponential, so attaching a factor of d by ds, and in fact we're going to move the negative out right away, so subtracted by and then a r squared multiplied by 1 plus 2i h bar a over m times s to the power of negative 1. Okay, so now let's multiply stuff. So this is going to give us 2a over pi to the power of 1/4, and then negative half times 1 plus 2i h bar a s over m to the power of negative 3/2, and then multiplied by the derivative of this. So this is going to give us 2i h bar a over m, and then multiplied by the exponential. And then over here we have this front term, which is just psi naught. So we're going to be subtracting by psi naught times a r squared times negative 1 plus 2i h bar a s over m to the power of negative 2 multiplied by 2i h bar a over m. That should be correct. Yeah. So now we can rewrite this a little bit to make this a little bit nicer. So we have, let's see, negative 2a over pi to the power of 1/4, 1 over square root 1 plus 2i h bar a s over m. So I'm taking away a square root term, and then exponential negative a r squared 1 plus 2i h bar a s over m. And then we have this 1 plus 2i h bar a s over m, the remaining term. So we're taking away a factor of negative 1/2. So what we're left with is negative 1. And then we have 1/2 multiplied by 2i h bar a over m. And then we're adding psi naught a r squared 1 plus 2i h bar a s over m to the power of negative 2 multiplied by 2i h bar a over m. Simplifying this even more, this front term is just psi naught, so we have negative psi naught, and then let's see, the 1/2 cancels with the 2, so we have I h bar a over m times 1 over 1 plus 2i h bar a s over m. And then we're adding, let's see, psi naught of 2i h bar a squared r squared over m times 1 over 1 plus 2i h bar a s over m squared. Is that correct? 2i h bar a squared r squared all divided by m. Yeah. So now let's verify that this is in fact true. So what we're going to have is the left side of negative h bar squared over 2m multiplied by the second derivative of psi with respect to r, which is going to be this. And we're trying to see if this equals I h bar, partial psi with respect to s, which we have over here, which is going to be equal to this. So now it's just a matter of verifying whether or not these two expressions actually equal the same thing. So at the front, let's see. The positives, two negatives make a positive, 2 cancels at the top. We have h bar squared a over m, and then 1 over 1 plus 2i h bar a s over m times psi naught of r comma s. Is that correct? 2's cancel, h bar squared a over m, yeah. And then we are subtracting by, over here we have 2 h bar squared a squared r squared over m times 1 over 1 plus 2i h bar a s over m squared times psi naught of r comma s. Is that correct? The 2's cancel, so we have 2 h bar squared a squared r squared and then m at the bottom, yeah. And then this is evidently supposed to equal, so at the front we have, let's see, the 2 i's make a negative which cancels out with the positive, so we have h bar squared a over m, 1 over 1 plus 2i h bar a s over m times psi naught. You know what, I think I made a typo here by forgetting to include the psi naught at the front. Actually, the psi naught's already there. So psi naught of r comma s. So the first term already matches, which is nice. And then subtracted by, because the 2 i's make a negative, and we have 2 h bar squared a squared r squared over m times 1 over 1 plus 2i h bar a s over m squared times psi naught of r comma s. So these two do indeed match. This term matches this term matches this term right here. So with that, the Schrodinger equation has been verified, and this is indeed, in fact, a valid solution for our free fall particle. And with that, we're done with the first part of this extremely mathematically tedious problem. Okay, so the final part of this wants us to find the expectation value of x. So to do that, we can recognize that we can write it as an integral from negative infinity to positive infinity of the magnitude of psi squared multiplied by x dx. If we look at psi, we see here that there's a complex exponential at the front, so that automatically cancels to 1 when you take the magnitude squared of this term. So what we're left with is that the magnitude squared of psi is actually just equal to the magnitude squared of psi naught of x plus half gt squared comma t. So we have what psi naught actually equals. So if we take the magnitude squared of this, this is going to give us 2a over pi to the 1/4 squared, gives us square root 2a over pi. Then we're multiplying 1 over root 1 plus 2i h bar at over m by its complex conjugate, 1 over square root 1 minus 2i h bar at over m. So that's going to give us 1 over root 1 plus 4 h bar squared a squared t squared over m squared. Because when you have a plus ib multiplied by a minus ib, the final result is going to be a squared plus b squared. So what we're doing is taking the complex magnitude of this term. Next, we have the exponentials, which is going to be negative a x plus half gt squared squared over 1 plus 2i h bar at over m plus negative a x plus half gt squared squared 1 minus 2i h bar at over m. So then we use distributive property, 2a over pi, 1 over root 1 plus 4 h bar squared a squared t squared over m squared. And then the exponential, and this is going to give us negative a x plus half gt squared squared. And then at the front here, this is going to give us, let's do it like this, 1 minus 2i h bar at over m plus 1 plus 2i h bar at over m. And then at the downside, this is going to just be 1 plus 4 h bar squared a squared t squared over m squared, because once again, a plus ib multiplied by a minus ib is just a squared plus b squared. This gives us a final result of root 2a over pi multiplied by 1 over root 1 plus 4 h bar squared a squared t squared over m squared. And then our exponential, negative a x plus half gt squared squared and then 2 over 1 plus 4 h bar squared a squared t squared over m squared. So the expectation value of x is then just going to equal, so we take out all the non-x values, so root 2a over pi comes out, and we also have 1 over root 1 plus 4 h bar squared a squared t squared over m squared that comes out. And then we have our integral from negative infinity to positive infinity of x times the exponential, negative a x plus half gt squared times 2 over 1 plus 4 h bar squared a squared t squared over m squared. So now our goal is to actually solve this integral to find the expectation value of x. Okay, so at this point I have a very painful integral that I can simplify very easily via u sub, just as we've done so many times before with this type of integral. If we have an exponential of something that has our variable of interest, but it's in a function, we can use a u sub and directly substitute with that function. So I could say u is equal to x plus half gt squared, in which case du is just equal to dx, and x is equal to u minus half gt squared. And I can create this new integral set, which is going to be the expectation value of x being equal to the square root of 2a over pi times 1 over root 1 plus 4 h bar squared a squared t squared over m squared. And then, whoops, that's a bit of a messy line. Let's do that. Integral from negative infinity to infinity of u e to the negative 2a u squared over 1 plus 4 h bar squared a squared t squared over m squared, subtracted by 1/2 gt squared e to the negative 2a u squared over 1 plus 4 h bar squared a squared t squared over m squared du. And then immediately I can split this into two different integrals, and hopefully you see here this exponential term is an even function, this u is an odd function, so the combined product is going to be an odd function, and this is a symmetric integral, so this combination automatically just integrates to 0. So the expectation value of x is going to equal the root of 2a over pi, 1 over square root 1 plus 4 h bar squared a squared t squared over m squared. And then we have our integral from negative infinity to infinity of, at the negative at the front, 1/2 g t squared e to the negative 2a u squared over 1 plus 4 h bar squared a squared t squared over m squared multiplied by du. And at this point, this is a Gaussian. So once again, as I've said many times before, you should know how to integrate a Gaussian at this point. If you do not, there is sort of, how do I say this? Very early on in the textbook, back in chapter 1, I think one of the very first problems that we actually did was an overview of how to actually solve a Gaussian. So if you don't remember that, or at least if you're not comfortable with how to solve a Gaussian, you should go back and look at that, because this is just a Gaussian. We're going to encounter Gaussians more and more often as we go deeper into the textbook. So at this point, I'm not even going to bother doing the Gaussian, or I'm not going to bother solving it out, because I just feel like it's too much of a pain to write it out and solve everything. So I'm just going to write out the answer for this. So what we're going to get is the negative root of 2a over pi multiplied by 1 over the square root of 1 plus 4 h bar squared a squared t squared over m squared. And then we have 1/2 gt squared, which comes out as normal. And then we have the square root of pi over the square root of 1, this is going to be 2a over 1 plus 4 h bar squared a squared t squared over m squared. So at this point, what we see here is that the root 2a cancels with this, the root pi cancels with this, the root 1 plus 4 blah 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 cancels with the reciprocal of this, so this whole thing cancels. What we're left with is negative 1/2 gt squared, and this is equal to the expectation value of x. And finally, we're asked to comment on this, and the comment that we can give is that this is basically just equivalent to the traditional kinematic equation for motion, because remember, in kinematics, we know that x is equal to x naught plus v naught times t plus 1/2 acceleration t squared. So if we have a ball that's dropping in free fall due to gravity, where a is equal to negative g, and it's initially dropping from a position x naught equals 0, and it has an initial velocity v naught equals 0, then the final position x at time t is going to equal negative 1/2 gt squared. And that's exactly what our expectation value equals. So what we've done here is we've treated a very easy problem in kinematics as a quantum mechanical problem by defining its wave function instead, and made it pretty much significantly harder. So obviously this is sort of the reason why we don't typically begin with quantum mechanics, even though quantum mechanics technically is a more accurate version of how everything happens. We don't necessarily want to use it in classical mechanics and on macroscopic scales, because even though we get answers that are correct, they sort of become sort of infinitely harder to actually do. But regardless, this is just sort of a very nice sanity check, because it's showing us that the quantum mechanics that we're learning here agrees with the classical mechanics that we've learned before, way back in the introduction to physics. So that's nice, because that sort of shows that even though quantum mechanics seems to be this big crazy thing that has a bunch of different fundamental principles, sort of the fundamental results that we actually get still do agree. So there is sort of linkage with the classical mechanics, which we're more comfortable with. And because of that, we aren't sort of losing touch with reality, as I'd like to say it, just from like doing all these wave functions and treating things without really understanding what's physically actually happening. And with that, we are done with 2.51.